A motor that uses less electricity, requires no rare earth elements and has an efficiency of nearly 100%. Sounds almost too good to be true, doesn't it? That's exactly what the American company C-Motive is promising now. And this is not a standard electromagnetic motor, the kind that powers virtually all devices nowadays. This is an electrostatic motor. It appears to be breaking all previous records and is already being tested by the first companies. How C-Motive managed this breakthrough and whether the motor actually has the potential to replace existing technology, you will find out in this video. And with that, Guten Tag, which means hello to the German science guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's. The principle behind these motors is actually very old. Over 270 years ago, Benjamin Franklin developed the first electrostatic motor. And although the first model was built as early as 1750, the electrostatic motor never really caught on, at least not on a large scale. Instead, most devices today use other types of motors. From electric toothbrushes to cell phones to electric cars, virtually every electric motor we know today is electromagnetic. So before we discuss how C-Motive managed to make this leap after all, we first need to clarify a few basics. What exactly is the difference between electrostatics and electromagnetism, especially when we talk about motors? So the difference between electromagnetic and electrostatic motors lies in the force used to convert electrical energy into mechanical energy. In an electromagnetic motor, there are two magnets. The stator, which is a stationary part of the motor, is a permanent magnet or an electromagnet. And the rotor, which is a moving part, is an electromagnet with coils through which electrons flow. The stator's magnetic field now exerts a force on the electrons. More precisely, this is the Lorentz force. It acts on moving charges in a magnetic field. You may be familiar with the left-hand rule, which describes the direction in which the force acts. And this Lorentz force now causes the rotor to rotate. This generates mechanical energy. However, the Lorentz force depends on the direction of the current. If it were always the same, the motor would simply come to a stop at a certain point. To ensure that the rotor can rotate continuously, the direction of the current must be changed repeatedly. In contrast, the electrostatic motor does not require magnetic fields, but only electric charges. The principle behind this is the Coulomb force, also known as the electric force. Here, the rotor does not move due to the interaction between magnetic fields, but rather due to the interaction between electric charges. Basically, there are different types of electrostatic motors, but the basic principle is always similar. Once again, there's a rotor and a stator. The stator has electrodes to which a voltage is applied. This creates an electric field that varies spatially. The voltage is negative at one electrode and positive at the other. There are now two possibilities for the rotor. First, a voltage can also be applied there, creating an electric field. Or the second possibility is that the electric field of the stator causes the charges in the rotor to shift, which in turn creates an electric field in the rotor. In either case, however, the electric fields of the rotor and the stator are spatially offset. Since this is not very energy efficient, the rotor rotates to compensate for the misalignment between the fields. By skillfully switching the voltages, a continuous rotational motion can then be generated. In contrast to an electromagnetic motor, an electrostatic motor requires only a relatively low current, but in return a much higher voltage in the kilovolt range. When the motors are used for applications where only low speeds or even a fixed position are required, this is a real advantage. Due to the low current, little energy is lost. In addition, the motors can achieve high torques despite their low weight. Other motors require additional gearboxes for this and are therefore less efficient. Electrostatic motors aren't really anything new. They are already being used in small applications such as very small pumps. The construction of magnetic components in electromagnetic motors is in fact extremely difficult at such small scales. So if you need motors in the milliwatt range, electrostatic motors are the way to go. But on a large scale, there are still some issues with this, which we will of course look at shortly. But first, let's examine why it's worth researching such electrostatic motors. Today, electromagnetic motors are the standard, and they really do work great. but there are still some issues. The biggest problem is likely the materials needed for the motors. More specifically, copper and rare earth permanent magnets. China dominates the extraction and processing of rare earth, and that leads primarily to dependencies and difficulties in the supply chain. On top of that, the entire process consumes an enormous amount of water and produces toxic chemicals. And then there's another problem with the copper coils. In electromagnetic motors, the high current simply generates a lot of heat in the coils. This means energy is lost here in the form of heat, which can then no longer be used for motion. As a result, the motor becomes less efficient, and in some cases, the coils even need to be cooled. And that's where the electrostatic motors have a major advantage. They achieve high torque at low speeds, and electrostatic motors have no magnets or copper coils, and consequently no rare earth elements and no complex cooling systems. And because almost no energy is lost as heat, the efficiency of electrostatic motors can theoretically be close to 100%. This saves a significant amount of rare and expensive materials and results in very high efficiency. So much for the theory behind the electrostatic motors. Now for the practical side. Research on electrostatic motors has been going on for a long time. As mentioned earlier, there were already other electrostatic motors on the market, though in completely different application areas than electromagnetic motors. Until now, electrostatic motors could only be used on a small scale in so-called micro-electromechanical systems, such as small drones or robots. The reason why the technology has failed in large-scale applications so far is air. In electrostatic motors, air is used as a dielectric. A dielectric is simply a material that conducts electricity very poorly. Nevertheless, electric fields can exist within the material, and this is then used, for example, between the stator and the rotor. While this works with air, it's not really ideal. This is mainly because an electric field in air cannot store very much energy. If the electric field becomes too strong, charge equalization occurs, essentially a short circuit. And that is why this principle has so far only worked reliably in such microsystems. As soon as the motor gets larger, air is no longer suitable as a dielectric. So an alternative to air as a dielectric is definitely needed. And this is where C-Motive comes into play. The American startup appears to have found a solution to this problem. This should allow the motor to function even on a macro scale, and according to C-Motive, be hundreds of times more powerful than all previous motors of this type. And all of this is because they have found a dielectric that works much better than air. It is a liquid, and of course C-Motive doesn't make it all that easy to find details about it. What is clear, however, is that the new dielectric is said to meet all the key requirements. At the top of the list, a high permittivity. This means a material stores electrical field energy well and can dissipate energy as heat. What we definitely know about C-Motive's liquid is that it is an organic liquid with a relative permittivity in the 20s. For comparison, air has a relative permittivity of 1. As a rotor and stator, C-Motive uses thin plates that are stacked alternately on top of one each other. The rotor plates have alternating positive and negative charges on their surfaces. The stator plates have 3 phases, each driven by 3 different voltages, and when voltage is applied to these plates, the rotor plates begin to rotate. The voltage can be flexibly adjusted so that exactly the torque required for the application can be generated. By using more and more rotor plates and utilizing this dielectric fluid, the performance of the electrostatic motor has been significantly increased. And if you were paying close attention, you may have noticed right away, the new motor has no gearbox and no copper coils either. That's why, of course, it doesn't need a cooling system. Even without one, the motor remains 30 degrees cooler than an electromagnetic motor. And because almost no energy is lost as heat, the motor also has a higher efficiency, which also means greater range for electric drives, lower electricity costs for industrial use, and higher energy generation, at least according to C-Motive itself. And they promise even more. Unlike previous electrostatic motors, this motor is expected to be scalable up to megawatt scale in the future. Well, and then there was the issue of rare earth magnets and copper. Copper still needs to be applied to the plates in the motor, but significantly less than before. C-Motive states that they need 90% less copper for their motor. Since the electrostatic motor simply doesn't require magnets, it naturally doesn't need rare earth either, only aluminum, fiberglass and plastics. And all of these are reportedly to be produced domestically, so that the supply chain difficulties and dependencies on raw materials from abroad would no longer be an issue. So as you can see, the company has really high hopes for its new motor, and in fact the first pilot projects are already getting underway. two companies are currently testing the electrostatic motor. However, the focus for applications here isn't necessarily on electric cars. The motor is instead more for industrial use, for example in assembly lines, for robots, or in medicine technologies, especially the so-called position and hold applications. This is of course primarily because the motor is optimized for low speeds. That means up to 200 revolutions per minute. Beyond that, the motor loses efficiency. So all of this sounds pretty great, and I want to discuss with you now whether C Motors press releases can actually be trusted or if the electrostatic motor still needs a little more time. We will sort that out in the big hurdle of this video. Before that, quickly subscribe and turn on the notification bell so you don't miss any more videos, especially if you like videos with transparent sources, because that's what I do. In Germany we say Vertrauen ist gut, Kontrolle ist besser, which means trusting is good, control is better, a very German thing to say. And because I want you to have the control, you can always check all sources. So I will always put in here the number of the source I'm using at that moment, and then you can check it in the video description. Okay, let's get into the big hurdle. So C-Motive has apparently solved one of the biggest technical problems with electrostatic motors. However, before the great motor revolution, there are still a few technical and practical hurdles that need to be overcome. So one problem is the availability of electronics. Motors like those from C-Motive simply are not really in use. Consequently, there isn't a wide range of compatible electronics available, including systems to control the motors, for example. And that naturally makes large-scale production of the motors difficult. That said, it's a problem that can certainly be resolved if the motors gain widespread adoption. Furthermore, the motor is designed only for very low speeds. I already said that. At speeds higher than 200 revolutions per minute, the frictional resistance increases by square, meaning it simply becomes extremely high. As already mentioned, this limits the range of applications and reduces efficiency if you go too fast. And also relevant, if you want to increase the torque, you will likely have to use different fluids, which does increase the dielectric constant and by that the torque, but can also further reduce efficiency. And a few minor points that I also want to mention in the end, but are really minor in my view. First, to ensure the fluid function as well as possible as a dielectric, no dust or dirt must go in. So you have to work under extremely clean conditions when building the motor. We can do that, but of course it's a bit more expensive than if you don't have to take care of that. So as you can see, there's still a few points of criticism so far. Nevertheless, it must be said, C-Motive has already achieved a breakthrough in this field. The mere fact that two companies want to test the motor already shows that there could definitely be potential there. But what do you think of the electrostatic motor? Do you see potential for the future, and if so, in which area? Feel free to write your thoughts in the comments. Otherwise, we see each other next week again, because every week there's coming a video on this channel. And I say vielen Dank fürs Zuschauen, which means thank you very much for watching. Auf Wiedersehen, which means goodbye. Your Jacob.